Howdy. Today we're going to talk about how to graph rational functions. And our primary tool for that is going to be the limit. So this is really going to be an application of everything that we've been studying up to now with regard to limits. Let's do a little bit of review. A rational function is the ratio of two polynomials. And because P and Q are polynomials, that's going to give us an advantage in analyzing these rational functions because factoring is our friend. And polynomials are particularly susceptible to factorization. In particular, what we're going to find is that, first of all, the zeros of the denominator, q of x, are all going to be excluded values. And because they are excluded values, they are going to show up on the graph as either holes or vertical asymptotes. I use VA as the abbreviation for vertical asymptote. And then all of the zeros of P, except for the excluded values, are going to show up on the graph as zeros of R. I had to do a quick spell check to see whether or not it is more popular to say zeros, to spell zeros with an E or without, and it turns out it's about even. But I put an E in out of habit, so there you go. Well, in any event, the zeros of Q are going to be the excluded values, which means holes or vertical asymptotes, and then the zeros of P, except for those excluded values, are going to be the zeros of R. And that's going to give us a framework for sketching our rational function. Then to this framework, we're going to add also the limits at infinity, which are going to give us the horizontal asymptotes of the function, as you know. And then finally, if all of that is not enough to give us a really good sense of the graph, and it usually is, but if we need some more information, then we will plot other points as needed. But we're going to try to avoid having to plot other points, except maybe to check ourselves. So that's the basic plan for graphing our rational functions. We're first going to find the zeros of Q, which are going to give us the excluded values. Then we're going to find the zeros of P, which will give us the zeros of our function R. Then we're going to use the limits at infinity to give us horizontal asymptotes. And then we'll sketch the function unless we need to find some other points first. Let's actually see this plan in action. I want to consider the rational function R of x is equal to, let's call it f of x actually. F of x is equal to x squared minus 5x plus 6 divided by negative x squared plus 6x minus 8. And we remember our plan from the previous page. We want the zeros of Q. We want the zeros of P. And then we want the limits at infinity. Well, to get the zeros of Q and P, we need this in factored form. So our first order of business is going to be to factor. I want you to pause the video at this moment and factor the numerator and the denominator. Welcome back. I hope you checked your factorization by multiplying back. If you did not do that, pause the video again and check by multiplying back. Welcome back again. So if you have checked your factorization, then you got this as your factorization. Notice that the negative sign here could very well be wrapped up into one or the other factor. So if in the denominator you got x minus 2 times 4 minus x, well, that is clearly the same thing. Or if you got 2 minus x times x minus 4, all three of those are algebraically identical factorizations. Now at this point, many of you are going to be tempted to identify that common factor of x minus 2 there and to try to cancel it out. Do not do that at this time, because the x minus 2 factor is going to give us an excluded value. Once we've dealt with that excluded value, we'll go ahead and cancel out the common factor. But at this time, we're going to leave all the factors alone. Now that we have it in factored form, I'm going to first find the zeros of q. So I'm going to set the denominator negative of x minus 2 times x minus 4 equal to 0, which gives us two solutions, x equals 2 and x equals 4. These are the excluded values. And excluded values are going to show up in some way or another as a point where the graph does not exist. The question is, will that be as a hole in the graph, or will it be as a vertical asymptote? And to determine that, we are going to use the limit as our tool for distinguishing the excluded values. So let's take each excluded value in turn and use the limit in order to find the behavior. First, I'm going to take the limit as x goes to 2 of my fraction right here. And what I'm looking for is a value on the one hand or infinity or negative infinity on the other. So let's see what we get. When we take the limit as x goes to 2, we see that we have a common factor of x minus 2 that can be canceled. There's our moment for canceling that common factor. And now I can evaluate by direct substitution. So that gives me negative 1 over negative of negative 2, which gives me negative 1/2 right there. I failed to do something before I evaluated the limit that I should have done, that I kind of fuss about. So I apologize for that failure. I failed to check the form. And when I checked the form that I get for the original limit is 0 over 0, which indicated the common factor. And I guess the reason I was in such a hurry and failed to check the form is that I saw that common factor already, and I knew that I could cancel it. But I do want to point out the form here, because I want to remind you that the form 0 over 0 is an indeterminate form. And it indicates that there is some sort of common factor going on there that can be canceled. Well, how do I interpret the fact that I got negative 1/2 as a value? What this means for my graph, if I can do a quick sketch right here, is that for x's close to 2, my y values are going to be close to negative 1/2. So if this is negative 1 and this is 1 and 2, and my y values are going to be very close to negative 1/2. Not at x equals 2. At x equals 2, my fraction disappears, fails to exist. So I have to put a hole in the graph right here, but all of my y values around that hole are going to be close to negative 1/2. The fact that I have a limit indicates that there is a hole at the point x equals 2 and with the y coordinate of negative 1/2. And the limit tells me that. I spelled indeterminate wrong, didn't I? Yep. Let's write that again. Indeterminate. There. Much better. Okay, well, we're halfway done dealing with our excluded values. So far, we have taken care of the excluded value of x equals 2. And what we have discovered along the way is that my function f of x is in fact equal to the function x minus 3 over negative of x minus 4, as long as x does not actually equal 2. And we call this the reduced fraction because it has been reduced now to lowest terms. And because f of x is equal to the reduced fraction, it's f for x equals 2, and because I have already taken care of x equals 2, for the rest of our analysis, I am going to use the reduced fraction for f of x. This is the point where I can cancel out that common factor and ignore it from here on out because I've already dealt with the 0 x equals 2. All right, so let's take the limit as x goes to 4 and see what happens. When I take the limit as x goes to 4 of f of x, which is the limit as x goes to 4 of the reduced fraction for f of x, then when I check the form, I can see that my form is now no longer 0 over 0, but instead I get a form of 1 over 0. And that form of 1 over 0, as we discussed in class, is an infinite form. And it indicates that I am going to get either positive or negative infinity on either side of 4. But because my signs of infinity could be different on either side of 4, it also indicates that I must immediately split this limit up into a limit from the right and a limit from the left. And the equal sign doesn't make a whole lot of sense anymore, so let's fix that. There we go. So we're going to do limit from the right, and then separately we're going to do limit from the left. And because we have an infinite form, 1 over 0, we already know that the limit is going to give us either positive infinity or negative infinity, and the sign analysis is simply going to determine whether that's positive or negative. And for the sign analysis, I'm going to consider what happens when I choose values of x that are close to 4 but greater than 4. In the numerator, when I choose x's that are close to 4 but greater than 4, I'm going to get 1, or something really close to 1, which is a positive value. And therefore, I'm going to mark the numerator as positive. In the denominator, when I take a value that is close to 4 but larger than 4 and subtract 4 from it, I'm going to have a positive residue left over. And so when I take and divide a positive by the product of negative and positive, then I'm going to get a net overall negative, and that tells me that my limit from the right is going to be negative infinity. If we do the same thing down here for the limit from the left, then, again, my numerator is going to be very close to 1, which is a positive value, 4 minus 3. But down here in the denominator, when I take a number that is close to but less than 4, and I subtract 4 from it, I'm going to have a negative residue left over, and that's going to give me a net positive value, so that I'm going to get positive infinity from the left. This indicates that I have a vertical asymptote. And the equation for the vertical asymptote is the vertical line x equals 4. Well, at this point, we have a large amount of information. So let's take that large amount of information and let's dump it to a graph. To summarize what we found so far that we have a hole at the point 2, negative 1/2. So that's going to give us a hole right here. We also found that we have a vertical asymptote of x equals 4. And we found that as x goes to 4 from the right, f of x goes to negative infinity, whereas as x goes to 4 from the left, f of x goes to positive infinity. And so that means that on the left side of 4, my graph is going to go up to positive infinity. And on the right side of 4, my graph is going to go down to negative infinity. So this gives us a little bit of an idea of the shape of the graph, but we need some more information. Let's go back to our reduced fraction here. Remember that f of x is equal to x minus 3 over the opposite of x minus 4, as long as x is not 2. And let's take our reduced fraction and set it equal to 0 so that we can find the zeros. Now, if I set this equal to 0, I can immediately multiply both sides by the opposite of x minus 4, and when I do, on the left side, my denominator times 0 is still 0. On the right side, my denominator cancels. So really, f of x will be 0 only when the numerator is equal to 0. I'll say that again. A fraction can only be 0 when its numerator is 0. And so this gives us a single 0 at x equals 3. This is additional information that I can now use to fill in the graph, and I can now also start to connect the dots. Because I know that my graph is going to go out to infinity, and it is also going to go through the point 3, 0. Now, students will sometimes get confused because they will not pay attention to the work that they have done previously. Remember that this was our original function. And students will sometimes look at this and say, hey, look, I've got a 0 at x equals 2 because I've got a factor of x minus 2 in the numerator. But we have already previously discovered that x equals 2 corresponds to a hole in the graph because x equals 2 is an excluded value. Therefore, it cannot possibly also be a 0. So I'll say this really clearly so that nobody makes this mistake. Excluded values cannot be zeros because they cannot be points on the graph because they are excluded. Well, we have managed to find and deal with the excluded values. We have managed to find the zeros. And now the only thing left to find is the horizontal asymptotes. And we're going to do that with limits at infinity. We're going to take the limit as x goes to positive infinity of f of x, and the limit as x goes to negative infinity of f of x. And once again, we can use the reduced fraction and then appeal to the end model. Notice that the end model here is x on the top and negative 1 times x on the bottom, and that gives me negative 1. And if you remember what I said in class, that for rational functions, the limits from the limit as x goes to negative infinity will always be equal to the limit as x goes to positive infinity, and we have negative 1 for both. And this indicates to us that y equals negative 1 is a horizontal asymptote. So we go back to our graph here, and we put the line y equals 1 as a horizontal asymptote. This allows us now to really complete the graph, because I can see that my graph is going to come up, and like so, and then the graph is going to come down, like so. It's going to come close to the horizontal asymptote, and there it is. You may ask the question, will this function cross its horizontal asymptote? And the answer, surprisingly, is that it can be hard to tell just looking at the form of it, but it's very easy to tell if I simply try to find the values of x for which f of x equals -1. So to see if it crosses it, let's look for an intersection point. Does f of x ever equal -1? And so we set f of x equal to -1, again using the reduced fraction because we know already that x equals 2 can't possibly be a solution because it is excluded. And then we're going to multiply both sides by the denominator. And when I multiply -1 times negative of x minus 4, then I get this equation right here. X minus 3 equals x minus 4. And if I subtract x from both sides, I come to this mathematical equation right here. -3 equals -4. And if that equation bothers you because you say it is impossible, then you are correct. There are no solutions. And because there are no solutions, there will be no values of x for which f of x equals -1, which means that f of x will never cross its horizontal asymptote. Now, what I'd like you to do at this time is to pause the video and take the original function, f of x is equal to x squared minus 5x plus 6 over negative x squared plus 6x minus 8. And from the very beginning, I would like for you to walk through the process of, first of all, finding excluded values, then finding zeros, then finding horizontal asymptotes, and finally, giving that function a sketch. If you can do all of that without prompting from the video, then you've got this lesson. And if you can't do all that without prompting, then go back and look at the appropriate part, and come back and do it until you can do it without prompting. So your goal for listening to this video, to say that you've succeeded with it, is to be able to sketch this guy by finding excluded values, zeros, and horizontal asymptotes. And then, tomorrow in class, we're going to practice